This is the video lecture for week 13. In the last week, we have studied indefinite integrals. Now we study the definite integrals and also the two fundamental theorem of calculus. First, the definite integrals. For any function f which is defined on the interval a to b, the definite integral of f from a to b is given by this. You see that? The same indefinite integral, except that we assign the limits here, which are the values, endpoints of the intervals here. Note that the definite integral is denoted by this, and where in the definite integral we assign the limits to the integration sign. This is the same thing as the limit of the Riemann sum. So you know that this is the Riemann sum and this is the limit of that, and we have already seen that this is gives me the exact area under the curve above the x-axis from a to b. So when the limit exists, we say that f is integrable on AB. So we have to remember that the Riemann sum, that is, in this Riemann sum, the Greek letter sigma indicate a sum. Same thing that this indicates, that is integration sign, which is elongation. That means it is extended, or you extend this s, capital S, it becomes this sign. In fact, the integration sign is elongation. That means it is expanded, expansion of capital S. So this is the same thing, that is sigma indicates a sum, and this integration, or this which is the extra expansion of S, is also used for the sum. The lower and the upper limits of the integration AB, that is what the endpoints of the interval indicate, the endpoint of the interval. Dx in the integral corresponding to the increment delta x. So this delta x and this dx is the same thing. This is in Riemann sum, this is in the integrations, and this dx is nothing but the variable of integration. And note that the letter used for the variable in the integration, that is the dummy variable, is irrelevant, because the value of this what you call definite integral is always constant, that is number. It is not a function of x, remember this. So, and this fx is called the integral. So, a theorem here, if f is continuous on the closed interval, then f is integrable on AB. So, note that if f is continuous on AB and fx is greater than or equal to 0 on AB, then this definite integral represents the area under the curve which is greater than or equal to 0. That means the definite integral and limit of the Riemann what you call sum is nothing but it is area under the curve. Now we have one definition here, that suppose that fx is positive on the interval a to b, that is from here to here, right? And A1 is the area bounded between the curve and the x-axis AB. So that is this pink area. And suppose that fx is negative, you see it is negative, that is below the x-axis, opposite, that is above the x-axis positive. Fx is negative on B to C, from B to C, and A2 is that area, that is the blue. Then the signed area between y equal to fx and the x-axis for A to C, you see, from A to C is given by A1 minus A2. This is the sine area. So since A1 is up above, it is positive, A2 is below, then it is negative. The sine area between from A to C is given by A1 minus A2. A2 is minus because it is below. Then the total area is the area A1 plus the area A2. So look at it, sine area is A1 minus A2 and the total area is A1 plus A2. So what this definition says that the area is the signed area is the difference between any areas lying above the x-axis, any area lying below the x-axis, that is the signed area. While the total area is the sum total of the area bounded between the curve and the x-axis. So this is what the difference between the signed area and the total area. Some of the important what you call theorem here, that for any constant CD, that is this C and D, then definite integral a to b c fx d gx is, we can take this C out and D out, you see, C and D out. And then another rule, another theorem, for any C in AB, then a to b fx dx is same as a to c plus c to b. You see, we started with the same thing. A to c ended with c, and then you start with c, c to b. So we can split this what you call interval a to b as a to c and c to b, but c must be in AB. Another two important theorems here is that b to a fx dx can be written as minus a to b fx dx. Look at it, this a is what you call less than b. So this is a very important, that means if I change this, that is b to a, if you want to write in a to b, then there will be minus, you have to multiply. And integration of a to a fx dx is always 0. That means when you have a same limits, then the answer is always 0. That means the area will be definitely 0. So these are the examples here for evaluating the what you call given area interpretation of this integral. So these two. Evaluate the integral by computing the limit of Riemann sum, this, and then write the given area as an integral or the sum of the integral. So this is what, and this is the answer for this, and the examples of these we will consider in the live class. So this is the end of the first part of week 13. Then we will continue one more part of week 13 in the next video lecture. Thank you.